Hi everyone, in this video I'd like to introduce sketching the graphs of Cartesian equation in Mathematica. Let's say for example we have this Cartesian equation, sine of x times y equals x plus y. Then often it's put into a more standard form where the right hand side is 0. So that would be this equation. So we're going to sketch the graph of this Cartesian equation using Mathematica. So here's how the command goes, and the command is this contour plot. That's the command. So I accidentally showed it, and I type those equations into this form. So left hand side is the formula and right hand side is 0, and I have to use this double equal symbol there instead of one equal symbol in Mathematica. Instead of typing in number directly here, you can store in an A, and next time when you have to change the ranges here, you just have to change that and execute the cell here, and that's going to do it quickly, so you don't have to change all this number every time when you want to look at the different ranges. So that's how you draw the Cartesian equation. So if you run that formula, it's going to show you from -4 to +4, and it shows the graph roughly looks like this. So that's the equation. Here I'm doing the same thing exactly a different way, and it's often useful for sketching lots of different solutions. For example, in differential equation, solution sets are parameterized, this one set to some constant. So rather than typing in like this, I use this two variable function defined and called f, and notice how the syntax goes if you want to define two variable function with variable x and y, and this is how it's defined, and then you can call that down there like this, f of x, y, without this underscore, set equal to 0, and that's exactly the same thing. Then you will get this graph show up. So next thing is that I'm going to change this number to 1 or 2 and see what kind of family of curve we get. Often some different solutions of a differential equations are described in that fashion. So here's what I mean by the families of solutions. So not only we're plotting these functions set to 0, we can maybe change that number to 0 to 1 and sketch the graph of that Cartesian equation. So we're going to vary that constant c on the right hand side from -6 to +6, increasing by 0.5, and see what kind of function graph we have. So often this appears as a form of a solution set in the first order differential equation. So this is one way to plot those solution sets. So if you run that, you will see this family of different curves. If I go and point maybe somewhere here or there, that was a 0. As you can see, that's where our original solution 0 is. So when it's the negative 1/2, it's kind of solutions that's similar to that, but it's slightly changing as we change the parameter the further away. And this is where the c is a positive direction. As you can see, this is where it's a 2, and it's a part of where c is a 7/2, and so on. So one thing notice from this family of solutions that they never intersect each other, and that it's a part of an important theorem. We should call that as a fundamental theorem of ordinary linear differential equation. So that's solutions never intersect each other. That statement is very important, because if you think about a solution that passes through this point, once it passes through this point or here, there's no other curve that passes through that point, so it kind of tells us the uniqueness of the solution set. But this is the collection of all those families of the curves. Here I'm playing with a slightly different kinds of families, which does not rise as the solution sets of ordinary linear differential equations. So you will see something different. So I throw in c in more complicated places like that, but I still setting that c in the right hand side like this. See, as we vary this c, what kind of Cartesian graphs of the Cartesian equation, how they vary. So it's different. When I ran it, it kind of have that, parameterization and property. Around here they're not intersecting each other. That part's nice, but as you can see down there, they're collapsing down to one point. So if there is a differential equation that has this one adds up the solution sets, they're definitely not linear and ordinary. But even if you don't know what these differential equations are, this is purpose of this video is to show you how to sketch the Cartesian equation, and in this part here is the graphs of many Cartesian equation parameterized nicely by the C, and then this is how you're gonna sketch it nicely. Thank you.